Now here's the step-by-step process for regression analysis. You could see the ladder that I have constructed, and you would notice that I have suggested that you start at the bottom and then make your way upwards. The first step is to first understand the question. You always would be given a question, and then you have to answer that question. For instance, um, is fertility rate higher in low-income countries than otherwise? So you completely understand the question, and by understanding the question, I mean you look at the factors that may be responsible or contribute towards the higher or lower or whatever the fertility rate may be in a particular country. So income and health and fertility and mortality and presence of disease or otherwise, all these things matter in answering this question, and therefore the first task would be to understand the scope of the question, the breadth of the answer that needed, and how deep you have to go in determining the answer. So once you understand that, then you look at the fact that do you have any data that you can start working with, and if you don't have data, then you have to collect it. And before you collect the data, this first step is here to define the population, right? For instance, in this case, you have to get if you answer this question for the whole world, then the entire global population is your population. Let's say if you were interested in determining the impact of fuel subsidies in South Asia on the price of wheat, then the South Asian population is your population to work with. And then from that population, you need to draw a sample. And in the previous example, I've shown you how we can, in the previous lectures, we've discussed how samples are drawn and what is the sampling error and so on and so forth. And then you collect data from that sample. The first step in analytics is to do the descriptive analysis, that is to run the descriptive statistics and look for the mean, the mode, the median, the standard deviation, the variance, and then you do all sorts of analytic graphics, plot the data and the key variables to identify the outliers, and so on and so forth. And then you can also do some hypothesis testing here to see, going back to the example of high mortality rate, if you were to have a variable called high income versus low income country, and high income identified as 1 and low income identified as 0, then you can conduct a hypothesis test to see if the difference in fertility rates is statistically significant using a t-test. Once that is done, then you look at the key variables of interest and conduct correlation analysis to see what kind of correlations exist between various variables, and then the last step would be the regression analysis. Now, with the advances in statistical methods, what has happened is that especially the statistical software such as Stata and R and SPSS and SAS, what has happened, and also Excel, sorry, how can I forget Excel? People, the researchers have now can run the analysis very easily because of the software, and what they do is they just jump straight to regression and bypass everything else, and that is the wrong way to do things. This is, jumping to the very last step is the wrong way. You must begin here. The first step is, in data analysis is collect data, and if you have the data, then start here with descriptive analysis. The more you learn in this step and in correlation analysis, the better it is for you to and you do a better regression model if you've gone through these descriptive statistics. In fact, they will serve as provide you with the intuitive basis for the relationships that you may first construct before you run the regression model. So the goal of the regression analysis is to go step by step on this ladder. Do not jump to the very last step, because now you may be an expert in R and you know how to do regression models in R or whatever software of your choice. Doesn't matter do things in a systematic way. A little bit about terminology. In regression, we always talk about the dependent variable, and we denote it as y, and it's called the dependent variable or the explain variable, or more commonly the response variable, and x is the independent variable, right? And we often say that y is a function of x, and by that we mean probably the fertility rate. Let's say fertility rate is a function of poverty, and that is, we don't know if it's high or low as a result of poverty, but we just say that it's a function of, and this fertility rate is y, and it's our dependent variable, right? And poverty is our explanatory variable. And I have taken an example from Jeffrey Woolridge's textbook, Introductory Econometrics, and in that we have this example where we say wage is equal to beta naught, which is a variable or a parameter, plus beta 1 times education. So this education is the explanatory variable again, and wage is the dependent variable. What does it mean? We're simply saying that wage depends upon education, right? So whatever your income is, wage, it depends upon education, and that's a regression model that you can estimate to find out the impact of education on wage. And notice that if a wage is measured in dollars per hour, let's say with the wage rate, and education is measured in years of education, then the beta 1, this variable parameter here, measures the change in hourly wage given another year of education, right? And I'll show you more in later examples. So again, going back to the notation, y is a function of x, and in the previous example this was wage and x was education. Now, in terms of regression, as I mentioned earlier, that we seldom talk about just one factor. We have more than one factor, so that's why you can have x1 and x2, which are two factors, and we're not limited to two variables. You can have multiple variables. You can have 10, 15, 100, 200 variables. Usually a model, a regression model has something like I would say 10 to 20, and in some instances 30 variables that we work with. So it wouldn't be just x1 and x2, it would go all the way up to say x30 in some instances. So y is the dependent variable and explained by other variables x1 and x2, which we call explanatory variables. So this y is a function of x1 and x2 is expressed in regression as y is equal to beta naught, and the beta 1 x1 plus beta 2 x2 plus the error term, and we'll explain, we'll go with it in an example. We'll show you what error means later. The betas are the regression coefficients that explain the relationship between the dependent variable and the explanatory variables, right here, and epsilon is the error term. Okay. Let's look at a model, a regression model, and I've estimated in R, so you can run this, and the data are also available on the website. So here's the R's term, but here's what we are saying, that the spending on food, which is Y, is a function of X, which is number of adults in the household, and we are using this data called expenditure, household expenditure, and it's available from the website. You can download it and run it. So basically we're saying that spending on food spending is a function of number of adults in the household, right, and how many adults live in the household. So food is equal to beta naught plus beta 1 adults plus error, and forget about the error for now. So this you can see here, this is the equation. When you run the regression model, this beta naught, which we call the conditional mean, becomes $29.4, and beta 1 is 34.73. So let me just write it here. This is our beta naught and this is our beta 1. So as I mentioned that the weekly spending on food, and let me just mention this is weekly food spending. I'll write it here. Weekly food spending. So weekly food spending is equal to $29.4 right here, right? Plus $34.73 for every adult in the household. So the model suggests that the base weekly expenditure on food is $29.4. And afterwards, each additional adult adds another $34.73 to the weekly expenditure. So a household with one person would spend 29.4 plus 34.73 multiplied by 1 equals to whatever the result is, and probably 30 plus 34, $64 approximately. Approximately $64 in weekly food spending. And if it were more than one person, let's say 2 adults, then we would have 34.73 times 2 plus, or let me just add plus here, the same 29.4 plus 34.73 on food spending. So let me write it again. For 2 per person household, y would be 29.4 plus 34.73 multiplied by 2, and the result would be whatever the dollars figure is. And that is regression model. Still, we are talking about just one influential factor, which is number of adults. Obviously, we're not looking at children and other important factors, but this is just to show you how a regression model is run. You would notice that the intercept here in R is the beta naught, and that's the 29.4 value that I got. And adults is the other variable for which the value is 34.73. I rounded the 7.7262 to 0.73. I have highlighted this 2 values here, which is called the t value, and I'll explain it later as to why this thing matters. The other important thing is the adjusted R squared, which is 0.15, or in percentages terms it's 15.04%, and this is the goodness of fit statistics, right? And we'll discuss this later. Okay, let's look at another example. In this example we have the data for the average height and weight for American women aged between 30 and 39. It's not, I think, a real data set, but just let's work with it. The height is represented in inches and the weight is represented in pounds, and the weight is plotted here on the y-axis, and the height is plotted on the x-axis, which is right here, and you could see the relationship is shown as a linear relationship. And then the descriptive statistics, I just typed summary and the variable and the data set's name, and I got the descriptive statistics on weight and height. Notice that the mean weight is 137 pounds, and mean height, or the average height, is 65 inches. We do the same thing with this data set. We believe that weight is a function of height, and then you translate this into a regression model. It becomes weight is equal to constant, or beta naught, plus beta 1 times height, right? Same thing written up here. And this is how the output from R looks like. And you have the intercept which is the beta naught, which is negative 87.5, and height is 3.45. What does it mean? It means that the weight of a woman is equal to 87.5 pounds, but this is negative 87.5 pounds plus 3.45 times height in inches. Now, the reason it's negative is because if you put 0 here, then you have negative 87.5. But then again, no one is of 0 height, right? The minimum height for a woman was noted as 65 inches, right? If you look at it here. So let's plot this number for here. So I would just write this equation again, which is equal to minus 87.5 plus 3.45 multiplied by, once again, 65. Okay, so if I were to calculate this with my calculator, I have 3.45 times 65 plus, or minus actually, 87.5, so minus 87.5, and the result is equal to 137 pounds. So my model is predicting that the average height woman of 65 inches would have a weight of 137 pounds. And look, here our model is suggesting the same thing. And the actual data is suggesting the same thing. So we're very close. Good. And that is what regression model is doing. It says our initial hypothesis was that weight is a function of height. Remember, let me just take it to a highlighter here. Okay, so our initial hypothesis was that weight is a function of height. We turned it into a regression model. We said weight is equal to always beta naught, which is the conditional mean, conditional upon whatever variables are in the model. And we say weight is equal to beta naught plus beta 1 times height. And the regression model gave us the beta naught as minus 87.5, height being 3.45, and the adjusted R square is 0.99 or 99%. So this is a typical regression model, and it's an ordinary least square model because we still are working with only one explanatory variable. Now let me just quickly talk about the t-value. And t-value is very critical in regression analysis. Let me switch my pen from highlighter to the pen, and let me change quickly the color to blue so I can talk about this topic. And here we go, blue. Now the t-value, notice that there are as many t-values reported here as many variables or the parameters we estimated. So 2 parameters, the beta naught and the height, and the 2 t-values. And the t-values are used to determine if the estimated parameters are statistically significant. And when we say statistically significant, we want to know if they are different from 0, statistically different from 0. And there's a rule of thumb, and I don't want to go into much detail. You can read from the course materials that I have put on the website. The rule of thumb is that if the absolute value of the t-statistic is greater than 1.96, that is, if the coefficient is negative and then the value is greater than negative 1.96, and if the coefficient is positive, then the value should be higher than 1.96 or approximately 2, right? The rule of thumb is that whenever the t-value reported is greater than 2, then the estimated coefficient is statistically different from 0, and let me write it down, statistically different from 0. What it means is that there's a statistical relationship between the variable of interest, which is height, and the dependent variable. So whenever the t-test is greater than 2 or t value is greater than 2, then we can say that there exists a statistical relationship between dependent and the explanatory variable. Good. So weight does depend on height. Weight is indeed a function of height because we got a value of 237.85, which is greater than 2. Right. Okay. Now, if you remember the earlier lectures that I've given, I've shown you this graph many times. This is the standard normal distribution curve, and you could see that we have plotted it for degrees of freedom of 99, and the values are, and this is a one-sided left test. If the value is if you are conducting a two-sided test, let me show you the two-sided test first here. So what we are saying here is that whenever you get a value of 1.98 or 2, here's the two values. This is the tail of the rejection region. This is the upper tail and this is the lower tail. And you're saying that 95% of the time the value that you've got for your estimated parameter is not located here. Because if it is, then it's not statistically different from 0. And because it's greater than 2, positive 2, so it's here, or greater than negative 2, it's here, then it's in this extreme region, and the null hypothesis that it was 0 is rejected. And so for a two-tailed test, a 95% confidence interval require a t-test, t-value, t-value of at least 2 or 1.96. For a one-tailed test, if you could see here, this is the right-sided test. The t-value doesn't have to be that large. It could be even 1.66 because we are testing this one-sided. Here we are saying our hypothesis, underlying null hypothesis, is that the estimated parameter, the parameter is greater than 0, right? And when that is the case, and if you get a, let's say, a beta 1 of greater than 0, and the t value is greater than 1.66, right here, see this, then you can say that this is a statistically significant result. And indeed, the dependent variable is a function of explanatory variable. So what happens when this value is not greater than 1.66? What happens when it's lower than 1.66? Well, then it means that in this particular case that the parameter is somewhere here, and it's not statistically different from 0, and that means that there is no relationship between the two. So then we can say that in fact weight does not depend on height, and we would do that only if our t value was less than 1.66. Okay, good. So let's look at another example, and in this example we are now moving from one explanatory variable to a condition of multiple explanatory variables. And in this case we have we are modeling housing prices as a function of the size of the housing unit, the style of the housing unit, and other variables. Now the housing price is in thousands of dollars. So if the house price is, let's say, roughly $300,000, it has been divided by $1,000. So in the model, in the data set, it looks like 300, right? So thousands of dollars, we just took it and divided by 1,000, and this is how it looks like. This is often the case with large numbers. We divide them by 1,000. It doesn't really affect the analysis. It rebases it a little bit. And then in the analysis, you have to deal with a smaller number of zeros. Then in this case, you would have to deal with a large number of zeros. The number of bedrooms are modeled or are in the data set as number of bedrooms. If a house has 1 bedroom, 2 bedroom, then the house sits on a lot that is the size of the land, and that is measured in square feet, right? So the house could be on a lot size of, say, 40 feet by 60 feet, and that would be 2,400 square feet, right? That is the lot size. Now the square footage of the house could be different. For example, the house, each floor has, let's say if it's a 2-story house and each floor has 1,000 square feet, then the square footage of the house would be 2,000 SFT, right? That's the built up area, and that's the lot size. If the house is of colonial style, this is a categorical variable, then it is coded as 1, otherwise it's 0. We have also taken the natural logarithm of the price variable and the assessed value, that is the value assessed by the taxation department, and the size of the house and square footage in the rooms, right? And the first thing to do now that since we have the data set is do the descriptive analysis or descriptive stats, right? And you have 88 observations, number of houses in a data set. The average price is $293,000. Now I know this is not 293.5 because I have told you that it's divided by 1,000, so it's $293,000. The cheapest home in the data set was for $111,000. The most expensive home was for $725,000. And the number of bedrooms, the average number of bedrooms is 3.56. This minimum was 2 bedrooms, the maximum was 7-bedroom home. The lot size is 9,000 square feet as the average lot size. The smallest unit had 1,000 square feet as the lot size, and the largest unit was a humongous lot of 92,000 square feet. The built-up area, obviously, look how small it is. The average built-up area is 2,000 square feet. The smallest was 1,171 square feet, and the largest was 3,880 square feet. So you could see that the built-up area doesn't have that much of a difference between the smallest and the largest, but the lot size, you could see that there were some very large lot sizes. Now remember, colonial was coded as 0 and 1. If the house was colonial, it was coded as 0. If it were not colonial, it was coded as 0 and 1 otherwise. If you take the average of this, which is 0.69, it tells you that 69.3% of the homes were colonial. So whenever you have a categorical variable which is coded as 1 or 0, the average tells you what percentage of the data has 1 and otherwise. Okay. 69.3% of the homes are colonial. The average square footage is 2,000. The lot size average is 9,000 square feet. Average house is 3.56 bedrooms, and the average house price is $293,000. The correlations are, instead of getting a correlation in terms of a table, I have plotted correlations as in a graph, and this is called a scatter plot matrix. So you could see that here, this is the, let me change the color because everything is already here, red. So the size of the house in square feet, not the lot. You could see that the size of the house in square feet is from 1,000 to 4,000 square feet, and the house prices, this is the variable right up here, right? And the housing prices are between 200,000 and 800,000. Now here you could see that as the built-up area increases from, say, 1,000 square feet to 4,000 square feet, the price of the house also seen linearly increasing from, say, less than 200,000 to all the way to 800,000 square feet. In terms of the size of the lot, the relationship is not as pronounced, even though it's an upward relationship that you can see that the price increases with lot size, but it's not as pronounced and as linear, visibly linear as the impact, as the relationship between the square footage of the lot size, square footage of the built area, and the price. You could see that the impact of number of bedrooms, and since number of bedrooms are a discrete variable, this is 3, 5, and 7 here, you could see that there's a generally upward trend, but then it's hard to see from this graph. Okay, so here I have presented the relationship as a regression model, and OLS stands for ordinary least square regression. It's called ordinary least squares regression. And in the first model, labeled A, I only have one variable, which is number of bedrooms. And the model I'm estimating is that, let's see, price is a function of, let's say, bedrooms. And it becomes as price is equal to beta naught plus beta 1 bedrooms, which becomes price is equal to the constant right here, $72,200 plus beta 1, which is $62.02 times bets. Right. That is the model here. This is model A. Let me just write it down. This is model A. For a 2-bedroom home, you put 2 bedrooms here. But as I mentioned that in a multivariate analysis, more than one factor is influential. So in the second model, B, we not only kept the bedrooms, but we added the lot size. Right, lot size right here. So let me just clean it up a little bit so you can see the lot size written a little better. Here, let me just take this out. Here you go. So when we added the lot size, you would notice the impact of bedrooms have slightly declined. Initially, the model was suggesting that each additional bedroom would add $62,000 to the price. In the model B, it's saying, no, it's going to add $57,000 to the price, and each square foot would add $0.002, or roughly 0.002 times 1,000, which is $2.8. So let's see this 0.002. Let me just come here and 0.0028, and then you multiply it by 1,000, and this becomes $2.8. So each square footage, so each additional square footage contributes $2.8 to the price. So if the lot size increases by, say, 100 SFT, then the price goes up by 2.8 times 100, which is $2,800. Right? And obviously here we already know that each additional bedroom is adding 57.3. If we added colonial to the model, right here, you would notice that it has a negative coefficient, and minus 2.2 is basically minus $2,200. Colonial homes will sell for $2,200 less once we control for the number of bedrooms and the lot size here. And this was C. In D, in the fourth model, I have added the square footage of the property instead of the lot size. See this variable here, which is the square footage of the property, the built-up area, and it tells me very interesting things. And it tells me that each additional square foot would add 0.1298. So I multiply it by 1,000 because we have divided the housing prices by 1,000. So it tells me that each, let me just write it down up here, that if the built-up area increases by 1 square foot, right, the price of the property goes up by $129.8. And if you add 100 square feet, then it results in 129.8 times 100, which would be 12,980, or roughly $129,800. So the price of the property is very sensitive to the square footage, right? It tells us that for additional 100 square feet, the price can go up by $129,000. Let's look at the last model, and here I am modeling I've transformed the variable, and the dependent variable is the log of price, the actual price, not in thousands of dollars, which is basically the log of price is a function of log of square footage of the lot size plus the, or not the lot size, but the log of the built-up area, so plus the log of number of rooms and colonial, if the house is colonial or not. So we have three variables, explanatory variable, and this is the built-up area. So the built-up area log transformed, number of rooms log transformed, and colonial as 1 or 0, but no log transformation. Now you look at the model and we have the results here. Now here's an interesting thing, and I'll discuss this later in detail but let me just give you a snippet here, that when the dependent variable and the explanatory variables are log transformed, the estimated coefficient, as is the case here, is called elasticity. So basically, for a percentage increase in lot size is accompanied by a 0.84% increase in price of the housing unit. So this coefficient is very different from the coefficient you've seen earlier, here as in here, or square footages as here. It tells you the estimated coefficient is actually more like elasticity, which is a percentage increase in one variable as a function of a percentage increase in another variable. So a percentage increase in the price of in the size of the square footage of the built-up area, it results in a 0.84% increase in the price of the house, which is direct measure of elasticity. Same is the case with the number of rooms. A percentage increase in the rooms is accompanied with 0.038% increase in the price of the house. But obviously you realize that we shouldn't have log transformed rooms, because if rooms do not increase by a percentage, room increase by 1 or 2, there's a discrete increase in the number of rooms rather than a percentage increase in the number of rooms in a house. Also look at the colonial variable, and now it is 0.0618. If we were to multiply this 0.0618 by 100, then we get 6.18%. And what it tells us is that if a house is colonial, the price of the property would go up by 6.18%. But notice that I haven't reported in the t-test, but there's no star next to it, so this is not a statistically significant coefficient. So yes, there is a positive correlation we're capturing, but it's not a statistically significant correlation. And the adjusted R square is 0.548, or 54.8%. So the model fit is 54.8%.